is Jonathan.
My name is Karen.
My name is John, and we are ME Team 17. We will be presenting on our durability study of an ash drain pipe for circulating fluidized bed boiler, sponsored by GE Power. Our industry sponsor is John Power, and our faculty advisor is Vito Moreno.
GE Power designs boiler systems for power plants that include the circulating fluidized bed boiler. These systems utilize the ash drain pipe to remove fly ash material from the boiler in order to optimize its power generation. The goal of this project was to determine what feasible modifications could be made to the current ash drain pipe design to increase its durability. In the diagram, you can see the different components that make up the current design.
Here is our approach. For the ash pipe insulated in Cambodia, we found some problems. The gate valve is not functioning properly. The angular system is moved 52 meters closer to the boil. The insulation rod is left in the expansion joint. The upper pipe portion insulated at an angle with vertical line, and the right picture shows the insulation rod is being bending.
Our initial approach was to consider pipe configuration changes and the addition of insulation or refractory. After analyzing the feasibility of these possible modifications, we found that a component change would be the most beneficial to our current design criteria. In order to solidify this decision, we created a pew chart with criteria and their different weights. Although initially one of the main focuses was reducing the red glow of the pipe, this was no longer a focus, and so it was weighted much lower than the other criteria. Although the insulation and refractory could decrease the outside temperature of the pipe, the disadvantages greatly outweighed the benefits. Instead, the most beneficial design would be one that could be easily adapted to the current design, as one had already been installed in Cambodia. GE would benefit from a recommendation that could be applied to the current installation, so we decided to focus on the expansion joint's movement capabilities, the spring hanger's optimal force application, and the proper function of the gate valve.
In order to determine the appropriate component changes to the system, the ash pipe was simulated in ANSYS. This allowed us to identify stress concentrations as well as validate expansion joint movement. Shown here is a summary of the loads applied to the system. Key things to note are the high component temperature of 861 degrees Celsius, significant boiler wall movement, as well as a significant ash weight of 4.8 kilonewtons. These conditions are representative of a worst-case operating scenario. This simulation and its results were used as a baseline to compare how our changes affected the ash pipe system as a whole. Key findings from the initial ANSYS simulation were that the expansion joint was undersized and the spring hanger could be adjusted to reduce stresses. From the image, you can see that the bellows of the expansion joint was fully compressed, and the chart shows that the expansion joint was exceeding the manufacturer capacity, deeming it in need of replacement. As shown in the plot on the right, adjusting the spring force had a dramatic effect on the piping stresses, identifying it as the main component to alter in order to reduce overall stress.
For solution of the gate valve, red is double set original one, green is one set new one. Table shows the data difference after using different gate valve. New design gate valve have plugged air wave design that can clean the ash jammed inside the pipe, and ash will not go to the path of the blade. And new gate valve have longer distance from electronics to ash pipe, which is a safer place with lower temperature.
After communicating with expansion joint manufacturers, 2 new expansion joints were designed, both of which include thicker, larger, and more bellow convolutions than the existing design. The thinner bellows will allow for the required movement without as large of a spring force as the thicker bellows. This will impact the spring hanger force necessary. Ideally, we would like a design that has the least impact on the overall system. Therefore, having an expansion joint that does not require a brand new spring hanger will be beneficial.
The optimum spring hanger force for each new expansion joint was determined through varying the spring force in ANSYS and choosing the force yielding the minimum piping stresses. This while paying close attention to the stresses in the Y portion of the pipe. This analysis yielded an optimum spring force of 6.9 kilonewtons for the thicker expansion joint and 7.54 kilonewtons for the thinner expansion joint. In both instances, piping stresses were reduced by at least 45%.
Here is about our summary. New design gate valve can produce safer place for electronics and can clean the ash jammed inside the pipe. The new design expansion joint can take much more movement in vertical and more movement in horizontal line direction. After all changes, the spring hanger can take less force, and the peak piping stress is reduced about half.